Okay, so this is the first of the more practical videos. We developed the theory for Taylor-Maclaurin series in the last video, and now we're going to go about finding a couple examples. So we'll probably try to look at two or three different ones from different places this time. So I thought the guidelines for finding a Taylor series in the book, we should discuss that first. So let's look. So first it says take several derivatives of the function to try to obtain um, a value for, or excuse me, an expression for the nth derivative. This is something that we've done back in Calc 1. We probably didn't do enough of it, but we did do it. So just taking the derivative like we've done in the previous videos, trying to recognize a pattern for s sub n of x. Remember, that's because the Taylor series for f of x that you're trying to look at in most of your problems, they're asking you to eventually come up with a series that goes from n equals 0 ideally. If you have to move the index, that's okay, but try to stay with 0. 0 to infinity of the nth derivative of c, where c is the center of the interval of convergence, divided by n factorial times x minus c to the n. And remember, c is 0 if it's a Maclaurin series. So you're trying to come up with that for most of your problems. Some of your problems, not all, make sure you read the directions. Most of them in the first week's assignments don't say this, but some of them then say determine the interval of convergence for that power series that results. And then some of them also say decide whether or not the series actually converges. So decide whether or not this side actually converges to be f of x. And remember, that's where we looked at that theorem that said that's true if the limit of the remainder term as you approach infinity is 0, right? And that remainder term you're going to have to stick in there as the Lagrange error bound thing, like f sub n plus the n plus 1 derivative of z over n plus 1 factorial, blah, blah, blah. So you might have to do that on some problems too. Probably not too many this week, though, but a couple. Okay? So we've already seen that. So let's focus on doing some more problems with number 1 here first. So first, we're in the second assignment out of 910, we're probably going to be doing more things like example 3. So let's just talk about example 3 first. So we spent a whole bunch of time in the previous video talking about the Maclaurin series for sine of x. So let's see if we can like adapt sine of x squared. So first, if we were following the step up here, we'd take several derivatives. So we start taking some derivatives. So we take the derivative of sine is cosine of x squared, chain rule 2x. There you go, first derivative. Then the derivative of this, dang it, we're going to have to use the product rule. So let's just trust them, and they get this from the product rule. So now you can imagine if you took a third derivative here and tried to start recognizing the pattern, this would just turn into a pretty awful mess, right? You'd have to take a product rule here and then derivative this, maybe combine some like terms. It's going to be pretty hard to see what's happening here. Then we'd have to plug in 0, but you know, that's kind of up to you. It's getting pretty messy. So the question is, can we take our plain old sine of x Maclaurin series and maybe adapt it to this one? That's a key trick. That's very nice. Okay, so let's see. Can we adapt it? Well, this is the thing we found for sine of x back in the last couple videos, right? That we were obsessing about almost. So if we plug x squared into that, will it work? And I think the answer is yes, it will. So since this guy just has x squared and it's just a composition, you can just plug x squared directly into the terms, term by term in the series. And then if you needed to write that down, let's see. Can we try to do that? I don't want to be too crazy here. So let's see. N equals 0. I don't know if this is going to come out so nice, but let's try it. N equals 0 to infinity. So it looks like we want the second, and then the fourth, and then the 10th, and then the 14th. This is definitely doable. And then down here it looks like it's like the odd factorial. So is that 2n plus 1 maybe? I'm just guessing. So I like to guess on these. You're definitely going to have to use like guess and check. So is that 2n plus 1 factorial? So under the first one we'd have 0, 1 factorial, yep. Under the second one it would be, let's see, 1, so that would be 3 factorial, yep, so there's the bottom. And the top, what would that be? We want the first term to be 2, I'm not sure, so looks like there's no, oh, it's alternating, so we need an alternating part. So -1, the first thing should be positive, so if we put in 0 there, that would be positive, right? So we go -1 to the n, and then we want the first thing to be x squared, so maybe like 2n plus 2 or something, I'm thinking. You know what I mean? Maybe x, I'm just guessing, let's see. 2n plus 2, if we put 0 in, we get squared. If we put 1 in, we get 4. Ooh, that's not quite right, right? We need it to be 6. Maybe it's 2n plus 3. I don't know, but this is kind of the way you have to do this, right? 2n plus 3. Now 0. Oh, no, that wouldn't be it, right? Maybe it's 4n plus 2. So you just have to fool around with these guys. So that's one of the things you're going to have to do on your problems. So let's go 4n plus 2. So if we put 0 in, we get squared, yep. If we put 1 in, we get 6, yep. If we put 2 in, we're supposed to have this, right? So we get 5 factorial, squared to be positive, and if we put 2 into there, we get 8 plus 2 is 10. Ha ha! That's what we were looking for. Sweet. Okay, so that one wasn't too bad. But notice, the key here was using an expression for a Taylor series, or excuse me, a Maclaurin series, this time it's centered at 0, that we already know. That's going to be really big, but not in your first assignment. Mainly in your first assignment, you're going to be trying to do this from scratch. So should I do a couple from scratch, and then we'll come back and do maybe one more of these? I think that'll be what we do in this video. So let me see if I can find one that we can do from scratch that's not too difficult. Let's see, what do I have? Another book here. Let's try this one. So let's call this problem 2 for this video, okay? So let's say that f of x, that we want to construct, let's do a Taylor series this time with a center of 2. Okay, so e to the x centered at 2. We've already kind of seen this Taylor series before, in like elusively in power series sections and stuff. But okay, let's just do the strategy. Brute force. So the first derivative, what is that? Oh, this is just e to the x, so it's e to the x. The second derivative, wouldn't it also be just e to the x? I don't think we need to continue the pattern for too long on this one, right? So let's just go dot, 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 and the nth derivative. Remember, always use those little wraparound guys there, otherwise that means to the nth power we want the nth derivative. It's still going to be the same old e to the x, no matter how many times we do it, right? So if we plug in 0 for any of these, we're going to get e to the 0. Oh, we don't want to plug in 0, sorry, we wanted to plug in 2. So if we plug in 2 for any of these, we're going to get e squared, right? Dot, dot, dot. The nth derivative of 2 for this function is still always just e squared. So if we try to come up with the series expansion then, excuse me, the series form, then it's going to be from 0 to infinity. Wow, that's pretty ugly. E squared is that part, and then this part is going to be n factorial. And then since this is centered at 2, it should be x minus 2 to the n power. Right, there you go. I mean, that one was pretty darn easy. You could go ahead and look at the interval of convergence by using the ratio test. So if this asked you, like back here, if it said now determine the interval of convergence, you could of course do that. I'm not going to do it on this one. It'd be a pretty simple ratio test. I'll just give you the answer. The interval of convergence is infinity on this one. So in other words, we could show, and we could also do step 3, and we could show that, we could do step 3 here and show this guy, show that the remainder goes to 0 if we took the time for that. And what you'd see is that this power series does indeed converge to e to the x for the entire negative infinity to infinity. So that series does converge down. That's what your calculator uses, except it only uses, like, I don't know, who knows, maybe a 20th order approximator or something like that. Okay, So there was a pretty simple one. Let's do another one. So I'm just going to stay on this same page now. All right. So a third problem. Let's see, what else can I find? Maybe one more brute force. Let's just do one out of your problem set. So I'll do one of yours. I'll do one of the odds. Let's see, number 5. Number 5 looks pretty good. I think it wants in number 5 for us to do f of x equals natural log. And it looks like it wants us to center this Taylor series at 1. Okay? So brute force, let's just start taking some derivatives. So we get 1 over x, right? And then the next guy would be negative 1 over x squared, right? And the next guy would be, what? We bring that negative 2 times negative 1 is 2 over x cubed. So it looks like it's alternating. Let's do one more. Fourth derivative would be negative 6 for negative 3 times 2 over x to the fourth. Looks like it's alternating, and I recognize that on top already. You might need to take one more derivative. I've already recognized that there's a factorial guy going on at top. So I'm going to say that, let me extend this page a little bit. So I've already recognized that this looks like a factorial that's alternating on top. So I think I know what the nth derivative is now. So the nth derivative of x, I think, is negative 1 to the n. Looks like there's some kind of factorial business going on top. And then on bottom we've got x to the n, right? 3, 3, 4, 4, looks like something like that. Oh, we needed to evaluate it at the center, right? So this guy, I'm not going to write it out. Do I have to? I hope not. So f prime of 1 is going to be 1. F double prime of 1 is going to be negative 1. F triple prime is going to be 2 over 1, 2. F quadruple prime is going to be negative 6 over 1, negative 6. So I think the next one would be 24. We did it. Okay? So there we go. So we're trying to say then that the natural log of x can be represented by the Taylor series. Let's see. So we're thinking of this guy, right? So what is that guy? Looks like we'll just stick it in. N factorial. Let's see. We've got an x to the n. Remember, then you take that and you divide it by n factorial. Let's be clear. I don't know if I was really right on this. Let's be careful. So the third power matches the bottom. The fourth power matches the bottom. So I'm pretty good about that x to the n. X to negative 1 to the n. Let's see, is that right? So if I put 1 in, do I get positive? Oh, I think that would be negative. So should we change this to like maybe, I don't know, n plus 1? I'm thinking so. Okay, n factorial. So 2. Do we have 2 factorial on top here? No, it's just that. So is it n plus 1 factorial? Let's see. Let's go down here. So here we've got 4, right? Like here n is equal to 4. And we've got what on top? That's 3 factorial. So what would we have to put in there? So the fourth derivative would be, let's just try to do it from our thing over here. So f fourth derivative. I always like to do it this way, just to check myself. So if we put 4 in, then we'd get that would be negative, right? So that's good. we get negative. And then 4 factorial is 24. Something wrong with that, isn't there? I think so. So let's see. So if we put 4 factorial, that's 4 times 3 is 12, times 2 is 24. So should it be, instead of n factorial, should we make this n minus 1 factorial? That's what I'm thinking. Okay, so if we put 4 minus 1 factorial, that's 3 factorial. 3 factorial is 3 times 2 is 6, times 1 is 6. Okay, there we go. And then I think we're good because we'll get x to the 4th. Sweet. Okay, I'm feeling better with this guy. So let's put this to n plus 1. Let's put this to n minus 1 factorial. And then, okay, so that's just the first part of that, of the power series, right? So we've got that part. Then we're supposed to divide by n factorial and also stick this guy on there. Okay, so let's go back. Oh, we're going to have to extend our page again, it looks like. So we've got, this is just the nth derivative. Now we're going to have to divide by n factorial, and then over here we have to put x, or are we trying to center this at 1, x minus 1, the n. So there we go. Can we simplify that at all? I think we can. So let's see. So I think that this factorial, if we expand it out, this guy can be written as n and n minus 1 factorial. Is that right? So that then these parts could cancel. And we get negative 1 to the n plus 1, x minus 1 to the n, and we've got what? Just an n down here, and an x to the n right here. So there we go. I think that's one way to do it. The book also simplified this another way. So another way to do this, besides like going directly from there to there, is to actually start writing out the terms, right? And go like, okay, the first term would be x minus 1, and then you'd have minus x minus 1 squared over 2 factorial, and the next one would be plus 2x minus 1 cubed over 3 factorial, and then the next one would be minus 6x minus 1 to the 4th power over 4 factorial. You could also go about it like that and then try to develop this guy that we got from that as well. So that's another way to go about it. I chose to do it this way. So just a couple options for your viewing pleasure. So remember, these guys, you can see that you'd have the 1 and the minus 1 and the positive 2. So you can see my coefficients for the nth factorial. So either way, you have to do this part. Once you do this part, you can try to go directly to the answer, or you can write out the Taylor expansion and then try to take that directly to the answer. So those are the two options I'm trying to present you with, okay? Let's extend the page one more time and do one more problem, I think. So one more problem. This time, instead of going so brute force, let's say that someone came along and said, we want a Maclaurin series for cosine of x. So of course a well-known Maclaurin series, but let's just say they're asking us to show it to them. So we could do this whole pattern and do it just like we did with that extensive problem when we did the sine in the previous videos, but let me show you a nice trick on this one. So do you agree that the cosine of x is equal to the derivative of the sine of x? Is that true? I think it is. So in other words, can't you just take the Maclaurin series that you already know for the sine of x and take the derivative of it term by term? So it was x minus x cubed over 3 factorial, right? And it went then it went plus, and it jumped to the 5th over 5 factorial, then it went minus and jumped another 2 to the 7th over 7 factorial, and so on and so forth. So can't you just take the derivative of that term by term? And I think the answer is, of course, yes. The derivative of x is going to be, of course, just x is just 1. The derivative of x cubed is just 3x squared, so that would be minus 3x squared. And you get the 3 factorial down here, and then the derivative of this guy would be 5x to the 4th. And then you'd have your 5 factorial, and then it would just keep going, going, and going. But you can see that this would simplify to 1 minus x squared, and the 3 over 3 factorial would cancel to become 2 factorial, right? And then the 5 over 5 factorial would be 4 factorial on the bottom after you cancel. So you can see that that is basically an expanded form of the Taylor series for cosine of x, and then you could try to go ahead and take that into this guy up here, which let's just do that. So then you'd have to start looking. So it looks like we've got 2 factorial and 4 factorial. I'm guessing that's going to be 2 to the n, 2n factorial. Looks like it's even. So if we put in 0, we'll get nothing. And remember, 0 factorial is 1, so that works. If we put in 1, we'll get 2. We put in 2, we'll get 4. See how that's going to work? And then I think something with x to the 2n maybe on top, too. Is it just x to the 2n? We could just check that. If we plug in 0, we're going to get x to the 0 is 1. Ooh. And then it's alternating, so we need to put a negative 1 to something on there. Is n or n plus 1 going to work? If we just go n, we'll get positive. Oh, it starts out as positive. There you go. So there is the compact form of the Maclaurin series for cosine. There is the expanded form. So we just used a nice trick on that one. So I hope you can do most of these with brute force. You can use a trick, though. If you can find a trick to be able to get this, go ahead and do that, like the ones I used. Okay, hope you found this useful. One more video for this lesson.